What if gravity, the force that holds literally everything together, isn't real? What if it's just an illusion? Well, we're going to dive into a pretty wild new theory in physics that asks exactly that. Okay, so where does an idea like this even come from? It all kicks off with this massive cosmic mystery. You see, when we look out at galaxies, the stars way out on the edges are just whipping around. They're moving so fast that our current understanding of gravity says they should just fly off into space. But they don't. So what gives? What's the invisible rope holding them in place? For a long time now, the conventional answer has been dark matter, right? It's this mysterious, totally invisible stuff that makes up, get this, a whopping 85% of all the mass in the universe. It's basically the universe's invisible scaffolding, the cosmic glue holding everything together. That's the textbook answer anyway. But what if that answer is just wrong? A recent paper on something called derivative frequency theory, or DFT for short, throws a real curveball. It suggests something pretty radical. What if there's no dark matter at all? What if the problem isn't that there's missing stuff out there, but that our theory of gravity is incomplete? All right, so to even begin to wrap our heads around this, we have to kind of tear down our picture of reality and rebuild it from scratch. And it all starts with this really cool idea the theory calls reality's fundamental Hume. Okay, first principle of this new idea, frequency primacy. Basically, it says, forget everything you learned about fundamental particles. Forget strings. The most basic, fundamental thing in the entire universe is this one single frequency field. Everything, you, me, this planet, the stars, we're all just different vibrations, kind of like different notes playing on this one cosmic instrument. All right, axiom number 2. This is where it connects to something we all know, energy. The theory says that an object's energy isn't just something it has on its own. Nope. It's completely tied to the local frequency of that field, right where the object is sitting. So if the local frequency goes up, the object's energy goes up with it. It's a direct link. So what does this do to the most famous equation in all of physics, E equals mc squared? Well, here's the cool part. It doesn't get rid of it. Instead, it says that E equals mc squared is what you get in a perfect situation, when that universal frequency field is totally flat and uniform. But if that field has ripples or changes, which it does, then the energy changes with it. So Einstein's equation isn't the whole story. It's just one perfect case in a much more dynamic universe. Okay, if everything is just a vibration in a field, then where the heck does gravity come from? This is where things get really, really interesting. The big takeaway here is that in this theory, gravity isn't a fundamental force at all. It's not some magical pull. It's what we call an emergent effect. It's a side effect, a consequence of how lumpy bits of matter, like planets and stars, interact with that fundamental frequency field. And the way this works is actually pretty easy to picture. You know how a bowling ball placed on a trampoline creates a dip, and a marble nearby will roll into that dip? It's kind of like that. A big mass, like the sun, creates a kind of dip or a slope in the frequency field around it. Other objects, like the Earth, aren't being pulled by the sun. They're just rolling downhill along the slope in the field. That rolling or that push is what we feel as gravity. And here's the truly elegant part. If you take this idea that force is just the slope of the field and you do the math, something incredible happens. When you zoom in to the scale of our solar system, the complex equations from this theory simplify down and become, well, they become identical to Newton's law of universal gravitation. It's not something they plugged in. It just naturally emerges from the core ideas. It's pretty amazing. And this has a huge implication. That famous number, big G, the gravitational constant, we've always thought of it as one of the fundamental constants of nature. But this theory says, nope. It's actually made up of other, deeper properties of this frequency field. Things like its stiffness or its elasticity. So G isn't fundamental at all. It's a symptom of something else. Okay, so with this whole new way of looking at gravity, let's circle all the way back to the beginning. What about those galaxies spinning way too fast? What does this theory say about the dark matter mystery? Well, the paper is pretty blunt about it. It says that what we call dark matter is just an effect of this frequency field. In other words, dark matter isn't a thing. It's not something we can ever find because it's not there. It's a phantom, a ghost that we invented because our theory of gravity was missing a piece. So why does gravity act differently up close versus far away?
It's because the real equation for gravity, according to this theory, is a bit more complicated than the one Newton gave us. It has these extra terms in it. That classic inverse square law we all learned in school, that's just part of the story. There's more going on that changes how gravity behaves over really, really long distances.
And here's the key. In our solar system, those extra bits of the equation are so tiny they're basically irrelevant. They're a rounding error. That's why Newton's simple law works so perfectly for launching rockets and predicting eclipses. But when you zoom out to the scale of an entire galaxy, suddenly those tiny extra terms aren't so tiny anymore. They start to matter a lot. And what do these extra terms do? They make gravity fade out much more slowly over galactic distances than we thought. And that provides just enough extra gravitational grip to hold on to those fast-moving stars at the edge of a galaxy. So the mystery is solved, not with invisible matter, but just by having the right equation for gravity in the first place.
Now, this all sounds great, right? It's a neat story. But for any theory to be actual science and not just philosophy, it has to do one crucial thing. Make a prediction that we can test. A prediction that could prove the whole thing wrong. And this is maybe the coolest part. The theory proposes a test, but you don't need a billion-dollar particle collider or a giant telescope. You can supposedly do it on a workbench in a lab with a pretty simple electronic circuit that engineers use all the time. And the prediction is incredibly clear, with no wiggle room. Here's the deal. Standard physics says if you test this circuit, you'll get a specific result, a classic bell-shaped curve. But this new theory predicts something completely different, a flat plateau. There's no in between. One of them is right and one of them is wrong. It's a clear, straightforward test. So this all leaves us with a really deep question to chew on. For hundreds of years, we've thought of the universe as being made of tiny little bits of stuff, particles. But what if that's the wrong picture? What if, at the most fundamental level, reality isn't made of tiny billiard balls, but of vibrations? What if the universe isn't built on matter, but on music?